Hey, good evening, everyone. My name's Alan Jones. I'm the president of RASC Vancouver. This year, I just took over the job. I'd like to welcome you all to our first
Hey, good
event
evening,
of the year. It's a
everyone.
kickoff for 2022. Uh, it's a joint event with SFU and RASC Vancouver. Uh, SFU Starry Nights. I'd like to first of all thank Haley, who's just stepped away from the camera, and Joanna Wu, who have organized this, and all of the participants and the many volunteers in the background who are working to support the streaming. Um, so the way we're going to work this is Haley and I will take turns introducing four speakers. The first speaker I will introduce is Bill Burnett. Bill Burnett's talking about the 10 must-see astronomy events for the year. I've known Bill for many, many years. He's a very engaging speaker. He's a delight to watch. He's spent years entertaining campers around BC. He also runs a planetarium at BCIT. Now I'd like to turn it over to Bill. I want to keep my part very short. Each speaker has 15 minutes. Take it away, Bill.
Okay, thanks, Alan. Well, um, I guess the first thing I should mention is that although I'm going to be talking about the top 10 items to be seen in the sky for 2022, I want to emphasize that every clear evening there's something great to see. So if you go out and it's not on one of these days, you look up in the sky, there's tons of things to see. There's always many Messier objects, double stars, variable stars. The moon might be doing something interesting, or a planet might be visible. There are many, many things to do. It's just that we have focused on these top 10 events of 2022. Now, you might say, well, this is just what Bill thinks is the best events of 2022. What about someone else? I've covered that. What I did was I asked the Canadian Space Agency to calculate themselves the top 10 events of 2022. And the Canadian Space Agency did that. And they sent me their list along with their representative, who is the Director of Media and Education at the Canadian Space Agency. So he's here with me right in this room here. So I'll introduce him now. This is the representative from the Canadian Space Agency. There we are, Bear. Mr. Bear. Now, Mr. Bear, do you have the list of the top 10 things happening in the sky for 2022? What is that? Oh, okay, can you is it time for me to open this now? Okay, so I will do that. Now, Barry, it's not necessary for you to be on screen all the time. There's plenty of food in the kitchen. Okay. All right, so I'm opening the paper, and here we are, 2022. The first one is, it's well into the year. So January, February, and a little bit of March. Nothing too unusual happening, but then at dawn, on the 31st of March, Mars, Saturn, and Venus will be very close together. Right? So you get up early in the morning, and out you go. And the constellations of the summertime will be visible at dawn, so that you'll see the summer triangle. Ophiuchus will be in the south, and in the ecliptic path there will be Mars, Saturn, and Venus making a little triangle. They will be seen together in the same field of a pair of binoculars. And these are my sky watching 10 by 50 binoculars. And so we'll be looking at all three of them at the same time, 31st of March at dawn. Now, if you have a little bit more power, it's possible to see them all in the low power field of a telescope. So if you own a telescope, take the telescope up, set it up, and the telescope comes with eyepieces. Select the eyepiece with the bigger number on it, which gives the lower power, slide that in, and then off you go. With a telescope, you can see Saturn's ring. It has a little tiny ring around it. Venus will be at some sort of crescent, perhaps gibbous. And Mars, that's a tougher one. You need a little bit bigger, better telescope for Mars. But even in a small telescope, it has a kind of a whitish fringe on the top, which is its polar ice cap, right? So those are some of the features we can see on these planets. But that's telescope stuff. For the binoculars, they'll just look like one very bright whitish star-like object. That's Venus. Saturn looks kind of straw-colored, and Mars looks kind of pale pink or golden colored, and they will be visible together. So that's number one. Number two, the Lyrid meteor shower, April 21st to 22nd. The Lyrids come from the constellation of the Hearth, right, which is in the summer triangle. So it's beginning to come higher in the sky at that time. So you go outside, choose a place where there's not too many lights and where it's nice and dark, and then sit down, maybe take a deck chair with you and put the deck chair up, lie back and look up at the stars, and you might be able to see as many as 15 shooting stars per hour. But that's not a guarantee, right? Because there's a number of factors that can influence it, exactly when you're observing, the height of the radiant above the ground, things like that. Generally, the later in the evening, the better for the shooting stars, because then the Earth, I happen to have a copy of the Earth right here, the Earth is pointing to where the meteors come from after midnight, right? So we get the onrush of them. Whereas if you're observing early, you're really getting the tail end of that. So the later the better for the shooting stars. Okay, so that's so now the next one is number three. It's a non-blue moon. Now this sounds kind of odd, and I asked Bear about this, but he's in the kitchen right now. I hope he made such a mess the other day. I'm not kidding. But anyway, he's not going to tell me anything about this. The non-blue moon is the opposite of the blue moon. Now, blue moon is the occurrence of two full moons in a single month. So you have a full moon in the first couple of days of the month, and you can crowd in a second full moon at the end of the month. This is the opposite. It's a new moon that begins in early April, and a second new moon is on the 30th of April. So there's the second new moon. Now, the thing about this is that you can't see it, right? You can't see the new moon, but you can see it a few days afterwards, where it is then a narrow little crescent with the Sea of Crises on one side. It's like a little blemish on it. So check that out in a good pair of binoculars or a small telescope. So there's the non-blue moon as the third item, April 30th. The next one is quite exciting. It's a total lunar eclipse, May 15th in the evening and 16th in the morning part. So the lunar eclipse will occur when the Earth, right here, and the moon, there they are, the moon goes into the shadow of the Earth, right? So the Earth has a big shadow, just like we all have a shadow. If you go out on a sunny day and put little stones on the sidewalk, and in the morning time, each one of those little stones will have a little shadow after it. I was doing that once, and then a guy was walking by and was looking sort of silly, right? Putting his little stones and pebbles down and have little shadows after them. And I realized it was the manager of the bank where I do my banking. So he thought maybe I'd flipped or something. Oh, it didn't turn out poorly though. He sort of forgave me about that. So anyway, there's the Earth, there's the moon. The shadow of the Earth is like a big ice cream cone, right? It's cone shaped, and the moon goes into that. Now, when the moon goes in, it becomes darkened or reddish, kind of like the color of this. Or yeah, kind of the color of that. And as that happens, right, the shadow of the Earth is formed on the moon, kind of like a target. If you follow the curve, you'll notice the curve of the Earth on the moon is much bigger than the moon. In other words, the shadow of the Earth is shaped like an ice cream cone. The moon goes into that ice cream cone shaped shadow, but the shadow is bigger than the moon's cross section. Therefore, the Earth must be bigger than the moon. And this can be seen just by observation and thinking about it when you're out observing an eclipse of the moon. It's one of the few times you can make a kind of a measurement of the scale of the solar system just by visual means without any equipment. In fact, Aristotle mentions this. So obviously, he didn't have a nice big telescope, right? But anyway, people went outside and looked, and they looked carefully, and then they interpreted what they saw, and so they even, with geometry, figured out the distance to the moon from the Earth, and getting a pretty correct result as well. Okay, so that's the first total eclipse, May 15th, 16th. It's in the evening time on the 15th. The next one, number 5, is June 14th, and it is supermoon. That's not exactly the same as a super duper moon, but it's pretty super. Okay, a supermoon happens when the moon is full near perigee, and perigee is its closest point to the Earth. So what happens is an ordinary full moon, very nice, but a supermoon, the moon's a little bit bigger. Now, you won't notice any difference. It's not like you can go and see craters naked eye because the moon is a bit closer. It's only a little bit closer. But still, the supermoon is of interest, especially if you're planning a night of observing. The moon will look a little bit brighter, and probably you won't notice its size difference at all. And there's an odd reason for that. And that is, the mind exaggerates the size of the moon in the sky. It's called the moon illusion. So the moon's size is determined by the psychology of cognition rather than the actual physical size of the moon. So it's not exactly, you're not going to notice anything, in other words, but that's what that is. That's number 5. Going down the list here. Okay, number 6, planets alignment, June 24th at dawn. At dawn, you look towards the east, Mercury will be low in the sky, then Venus, the crescent moon, Mars, Jupiter, and Saturn, all of them in a row. Now, why would they do such a dumb thing? Well, it's because the planets are going around on the ecliptic, right? And so the ecliptic can be thought of as like a race course in the sky. Right, now, that's not really the ecliptic, it's a horizon, but I'm just using it to illustrate. So the planets go around and around on this racetrack. Some of them are fast, some of them are slow. And there are times, though, when they get all bunched up, and that's an alignment. So what will happen is you'll see them all stretched out in a row during this period. Right? And now they're not really going to collide with each other, as some people might suppose, because they're all at very different distances. So Mercury is very close to us compared to Saturn. It is a kind of a trick to take a small telescope out and just go from one to another along there. Mercury will be quite close to the horizon and a bit of a challenge, but Venus and the ones above it should be easy to see. So there's the planets at dawn, June 24th. The next special event number 7, the Perseid meteor shower. Okay, but August 12th to 13th, there's a full moon near there. Oh boy, that's not so great. Bear, how come you arranged that? That was really, he can't affect that. Yeah, the Canadian Space Agency doesn't operate that way. But what's happening is the full moon is going to wreck some of the fainter Perseids, so you won't see as many as normal. The better Perseid displays are when the moon is in a different part of the sky, a new moon, or perhaps a third quarter or something like that. So the full moon will drown out some of the Perseids, but every now and then you get a nice, real bright one. So it's not a write-off, and you should go outside and take a look, maybe doing something else on that August evening. But definitely the full moon will be a factor for the Perseids. Now, the next one, number 8, total lunar eclipse, the second one. You're saying, hey, wasn't that on the last page? Yeah, that's right. There's 2 of them. You see, on average, there are 4 eclipses in a year, on an average year. 2 lunar and 2 solar, and they're separated by 2 weeks, because then the moon takes 2 weeks to go from full, which is a precondition for the a lunar eclipse, to new, when you can't see it at all, and that's a precondition for the eclipse of the sun. So that way, eclipses tend to line up with 2 weeks between them and in pairs, and that's the case in 2022. Now, the solar eclipses aren't so great for us, but the total lunar eclipse of November 8th before dawn, and there's actually a Western bias in this, because if you're in Eastern Canada, you won't see it very well because then the moon will set. But in Western Canada and Hawaii, this will be a good one to see, right? So Mr. Bear was complaining about that because as employee of the Canadian Space Agency. He lives in Quebec, right? So he's going, oh, no, no, no. But it had to be put on the list anyway. Sorry about that, Bear. Maybe you can come and visit. I won't charge you any more than a hotel would charge to stay with me. Okay, now, so we talked about that. That's November 8th. Then on December 8th, we're coming up on the end, number 9, Mars opposition. Now, Mars opposition is on that racetrack I mentioned where the planets go around and around. Every 26 months, we catch up to Mars and are equal to Mars on our orbit. So they're side by side. Mars gets a lot brighter, and so this will be the case. The oppositions of Mars mean that Mars, rather than looking like a tiny berry, will look a little bit bigger, right? And a little bit better in telescopes, especially good-sized scopes. Most of the discoveries about Mars took place in these years, these 26-month groups, right? And in the perihelic oppositions, as they're called. And so in 1877, the so-called canals of Mars were discovered, although there are none. In 1909, it was another one, and many discoveries were made. 1971, that was also a good year for observing. Now, there was a very close Mars approach in 2004, I think it was. And however, less was learned about Mars because of a difference, and that is we now can send stuff to Mars. So we have stuff on the surface of Mars, and so it's not, the discoveries are coming not so much from ground-based observation as from the space program. But if for some reason we couldn't send spacecraft to Mars, then these would be the opportunities to see Mars a lot better. Okay, but if you're not going to discover something, it's cool to see Mars with a little telescope, and it has sort of dark features on it. It looks sort of like continents, right? And then brighter features, and there's a little berry on top that's quite whitish, like a little layer of snow. Although the skiing there wouldn't be probably very good. Go to Whistler. Okay, so that is number 9, and number 10. A drum roll for number 10 is Bear. I can't read that. What does that say? Okay, Geminid meteors. Yeah, sorry. Now, the 13th and the 14th of December is the final event. That's the Geminid meteors. Now, this last Geminids, I understood from one of my observers stationed all over this planet, has said that they saw lots of Geminid meteors from a dark area. So these, the meteor showers are not all of the same magnitude. They're not all the same richness. Some of them aren't very good at all. But the Geminids have been sort of creeping up the list. They're getting better and better and better. And so it's possible that they might actually displace the Perseids at one point. But anyway, the Geminids are definitely something to look for, December 13th and 14th. The disadvantage is, at least in Vancouver, we tend to have not so great weather. Right. So if it's raining and stuff like that, you won't see any shooting stars, and you'll go home saying Bill's a fool. He didn't know what he was talking about. Right. But no, it has to be clear out. But if it is, give a look to the Geminids. So that is the end of my list. And I'd like to thank the Canadian Space Agency and Mr. Bear for supplying the list of the 10 top observational points to see in 2022. Thanks very much. And take our regards from Vancouver back to the Canadian Space Agency. Okay, thanks.
Thank you, Bill. Thank you for being almost on 15 minutes.
Okay.
Next up, I don't see William Wall's video. So there you are. Thank you. I'd like to introduce Dr. William Wall, who's a Canadian astronomer with a PhD from the University of Texas in Austin. He studied, he did postdoctorate work at the Goddard Space Center. Tonight, he's going to be telling us about the James Webb Space Telescope, which is very timely. Take it away.
Yeah, thank you, Alan. Happy New Year, everyone. Thanks for coming. Let's see if I can get this working properly. Let's see. Should be starting. There we go. I hope this is not blocked. Let's see. There. Okay. So, now the James Webb Space Telescope has been in the news a lot lately because it launched recently. It launched less than 2 weeks ago on Christmas Day. And here we see a picture of it. And over here we see a great web page that you can go to where you can track it in real time and see how close it is to its final destination, which is the L2 Lagrange point. I recommend checking that out. So the Webb telescope was developed by NASA in collaboration with the ESA, which is the European Space Agency, and the Canadian Space Agency. Yay, Canada. It was named after James Webb, the administrator of NASA during the Apollo years, although that name may change. As I said, it was successfully launched less than 2 weeks ago. Here it is on an Ariane rocket, which was launched from French Guiana. So the primary mirror, well, it talks about, it's a diagram telling you the different parts. This is the primary mirror. Down here is the sunshade, because this telescope must be kept cool. And the sun is down in this direction, it's downwards. Let's see, I don't know if people are going to be able to see this, but and the Earth and the Moon are down here this way. And this side is very cool here, where you have this sunshade keeping it cool over here. And there's the space bus here with the power supplies, and there's a solar panel underneath as well to power the telescope. So what will the James Webb Telescope do? Well, among these things here, included this is a diagram showing the look back time. You're looking back as you look further away, looking back closer and closer to the Big Bang. And the James Webb Telescope will be able to see the first galaxies forming, presumably. It'll study the formation and evolution of galaxies, as in this Hubble Deep Field here. The James Webb will do a better job of these fields. And you'll also be able to see the formations of stars and planetary systems. And in all of these cases, when you're looking this far back, the light that comes across the universe will be expanding into the infrared. And to see through the dust of these planetary systems, you need to look in the infrared. So you need infrared observations. So this telescope will be doing mostly infrared observations. You'll observe between 0.6, now 0.6 microns is actually sort of orange-red light, but it goes out to 28.5 microns, which is the mid-infrared. As I said, to observe these wavelengths, it has to be kept cold. So it has a large sun shield, as I mentioned, and it will orbit at 1.5 million kilometers from the Earth, at the Sun-Earth L2 Lagrange point. And here's the sun shield, and the telescope is on this side. The sun is back here. So this blocks any radiation from the Earth, the Moon, and from the sun to help the telescope keep cool in the shadow of this sunshade. The instruments, well, one of the instruments was supplied by Canada, or actually a couple of the instruments. We participated in the FGS as well. But these are near-infrared cameras, near-infrared spectrographs, and this is basically the wavelength range that it'll cover. These instruments are, like I said, spectrographs and cameras. This MIRI instrument is actually both spectrograph and cameras, which allows you to observe planets and protoplanetary disks and galaxies as well. So let's see here. I'm getting blocked by my own screen. Yeah. Before I show that comparison, there's this table here where you see the different wavelengths and apertures of different space telescopes. The Webb telescope is the successor to the Hubble Space Telescope and also to the Spitzer Space Telescope. And you see their wavelength coverage here. So the James Webb Telescope is, let's see if I can move this out of the way. Let's see, okay. Covers a longer wavelength range than the Hubble Space Telescope. There are the three instruments that the Hubble used, three of the instruments that it used, which only goes out to about 2 microns at most, roughly 2 microns. But the Hubble Space, the Webb Telescope goes out to 28.5 microns and doesn't go quite as short as Hubble. Doesn't quite go as far out as Spitzer Space Telescope. The main difference here you'll see is look at the size of the aperture here, 6.5 meters. It's much bigger than these other telescopes. It's the largest space telescope ever launched. This will give you better resolution, better sensitivity. Now the comparison of the two telescopes. The Hubble Space Telescope is about the same size as the Webb Telescope, but the primary mirrors are very different in size, as you can see here, and a puny human to give a sense of scale. So why have telescopes in space? They're expensive to build, expensive to launch, expensive to operate. It's because the Earth's atmosphere hinders observations. One way, of course, is that turbulence blurs the images, giving perturbed wave fronts, although adaptive optics techniques are improving, and they're actually quite good now. But the atmosphere adds noise to image, and it also absorbs the image because of opacity. And here's the percentage of opacity. See, in these bands here, there's much absorption by the atmosphere. This is from 0.2 microns out to what, 70 microns. And the Webb telescope observes from about 0.6 out to about 28 microns, covering much of this range here. And this range will be clear for the Webb telescope because it's in space. But we on the ground cannot see through these bands here. Visible light band is here. This due to these components of the atmosphere. If we could only remove those, it would be an observing paradise for us down here, except you wouldn't be able to breathe. Another advantage to being in space is you can see the entire sky. When you're observing from the ground, you cannot see the entire sky. We in the Northern Hemisphere, for example, can't see parts of the Southern Hemisphere. Now, after it was launched, I don't know if you can hear the sound. There's a cool soundtrack that you don't really need to hear, but so this is the telescope. It has to unfold to come out of the rocket. It's too big for the rocket. So this is like reverse origami. So you have the solar panel here. This is the sun shield, which unfolds after a few days. This has happened already, as a matter of fact, much of this. This tower separates the telescope from the sun shield. We have to flap, which uses solar radiation to help keep it oriented the right way. Sun shield is exposed, but it has to be stretched out on these booms after 6 days. So this happened like a week ago. Okay, then there's tensioning, because there are different layers of the sun shield to get better thermal isolation. The secondary mirror structure comes down. This is almost like a flower that's blooming in the sunlight, except this particular flower wants to stay out of the sunlight. So this is what happened yesterday. This is what's happened today. This happens very slowly because they wanted to make sure they do it correctly with no problems, no snags. And then in a little more than a couple of weeks, there'll be the orbital injection burn. It has to stop itself from going too far out. So again, we talked about this Lagrange point. What is this Lagrange point? This is what the telescope is heading for. It'll get there in about a month after launch. The Lagrange point is here. This allows the telescope to orbit the sun and yet keep up with the Earth. And it's not a stable point, so it has to orbit. It has to orbit around this Lagrange point. It also has to stay in the sun so that it has power. It's going to look at very faint infrared signals of very distant objects, so it has to be cool for that. And it's very cool on one side, minus 233 degrees Celsius on one side, 85 degrees Celsius on the other side. Okay, then they talk about the field of regard and the field of view. The field of regard is how far the telescope can look in the sky and what different directions it can look. 50 degrees in pitch, 10 degrees in roll, and it can also look around 180 degrees in yaw all the way around. It cannot see all areas of the sky in one particular position. After 6 months of orbiting, it will see all of the sky. And these are the fields of view of the different instruments. For the NIRCam, it's like 2 degrees for each of these squares, or 2 minutes, 2 arc minutes, I should say. And the science mission begins 6 months after it reaches L2 point. Okay. Now, what can you see with the Webb telescope? I have a little demonstration here, which is not entirely accurate, so you can take this with a bit of a grain of salt. I've used ground-based data. This was taken with a Gemini telescope. Gemini South. No adaptive optics. With adaptive optics, you can do as well as the Webb telescope, but it takes more work and you can't do certain wavelengths. What would the Hubble Space Telescope see? More or less, you'd see something like this. You can see the difference here, right? What would you see with the Webb telescope? You'd see much more detail. See a lot of filamentary structure here. This helps you figure out what's happening with magnetic fields. This happens to be molecular hydrogen they're looking at here. Gives you, again, ground-based Hubble Space Telescope, Webb telescope. Again, this is just a representation of that. So what about discoveries? Well, I left my crystal ball at the shop, so I can't consult it right now, but we could look at the Hubble Space Telescope discoveries to give us a rough guide as to what the Webb telescope might uncover in the universe. Again, we see this diagram of look back time. With the Hubble Space Telescope, help pin down the age of the universe, as well as the expansion rate of the universe, and those two are related. With the Webb telescope, we'll be able to look back a little bit further to maybe the first galaxies, and that will be important. The Hubble Space Telescope discovered that most major galaxies have a supermassive black hole in their centers. In the center of our galaxy, for example, there's one. Discovered two moons of Pluto, Nix and Hydra. You see them here. This is just to give you a rough idea of what we might be able to see with the Webb telescope, which will do an even better job. What's particularly interesting is the Hubble deep fields. They're impressive because these are supposedly empty fields that turn out to be filled with galaxies after looking at each of these space spots like 2 or 3 weeks, which means there are hundreds of billions of galaxies throughout our universe and the observable universe. And they were able to look back to like 600 million years after the Big Bang, but with the Webb telescope, that could be something like 100 million years after. Now, a huge challenge in astronomy is studying the evolution of celestial objects. That's because they exist on timescales much longer than human lifespans, much longer than the existence of the entire human race. So there were no cinematographers out there filming the whole thing, which is unfortunate. So like I said, no one's been filmed. There's no film recording the formation and evolution of real galaxies, which exist on scales of billions of years. However, now you can feel the suspense mounting. I'm sure you're on the edges of your seat. I know I am. Each Hubble deep field is like having a film frozen in time with its frames superimposed on each other. So what we can do is we can separate those frames by knowing the redshifts of the objects. For example, this particular object here, very red and is very distant, is probably the building block of the galaxy, one of the building blocks of galaxies. Whereas this is a complete spiral galaxy, and this is billions of years old. So we can have an idea of how galaxies evolved over time by separating these frames are like glued together. We can unglue them from one another and make our movie, make that film that I was talking about, which is a slightly oversimplified view of what's happening here. Now with the Webb telescope, you can do a better job. Here with Hubble, this is what you see when you look in the Hubble deep field. Here's a blow up of this particular galaxy. With the Webb telescope, you can see more detail. And this is just a simulation, of course. Let's look at that a little bit more detail. So here we see Hubble, Webb telescope. Look at that detail. And look at these little dwarf galaxies here. I assume they're dwarf galaxies. Let's look at that. With this, we have a better understanding, a higher resolution picture of what had happened in forming these galaxies. Now with Webb, of course, there'll be all kinds of discoveries that we can't even anticipate. So I make a prediction, which is hardly a bold prediction. There will be newsworthy discoveries from the James Webb Telescope before the end of the year. And I thank you for your time.
William, thank you so much. That was wonderful. I think we're all excited to see the images in maybe about 6 months. I'd like to introduce our next speaker is Lee Cummings. He is our chair of our Light Pollution Abatement Committee. He's doing some wonderful things and making some advancements in some urban dark sky awareness for some of our provincial parks. Hopefully, we can get some certificates happening over the next couple of years with applications, but creating awareness of light pollution abatement and the importance of dark skies. And I'm going to hand it over to Lee Cummings.
Okay. I hope I'm doing the right thing here. Where am I? Can you see my screen? Good, okay. Okay, hopefully the sound is up on everybody's thing here and we will get ourselves going. We will start this little presentation. Start from the beginning. I couldn't resist, sorry people. So we'll start with the bad side of LED lighting. As you know, first of all, I'm going to start with LED lighting simply because it's just the light pollution is just too big of a subject to do in 15 minutes. So I thought I'd take one that can be sort of see the evolution of where we can go with things. And so the ugly part of it is the early LED lights, they were only available in the blue end of the spectrum when they first came out. All the LED lights look bluish, and a lot of them still do. And I think a lot of people have heard that it's not that good for your eyes. But worse yet, it's hard on your sleep rhythms because the blue part of the spectrum is what actually wakes you up. I mean, that's from a biological standpoint, that makes sense. When the sky is blue, that's when you want to be awake. And so that's what stimulates the hormones in your brain that wakes you up and gets you going in the morning. That is for those of us who don't block it all off so they can sleep longer. So the ugly side is that, first of all, is that the first LED lights when they're first out were in that blue, and also they tended to be very high energy, like up into 5,000 or more Kelvin of power. Device screens were often still backlit far too much to the blue, so all devices, television screens initially, LED TV screens, computer screens, and even the cell phones, and that nobody could really dim them down. And also my pet peeve, and maybe anybody else with a smaller car, is the love of blue LED replacement headlights in people's pickup trucks and bigger vehicles that almost burn your eyeballs out when they come up behind you. My rear view mirror on my car automatically dims, but the side view mirrors don't. And it's sometimes risky when you're really kind of blinded to start playing around with things in the car to change it. And it is hard. Also, another thing is this new trend of putting LED floodlights in people's yards or in their driveways that shine out across the street or into the street. And there's a few in my neighborhood where if you're driving up, you're looking for your turn to get in because there's no street lights in our area, that you're just blinded as you come towards these lights. And it worries the hell out of me, and I slow right down because you don't know if someone's out walking their dog and stuff like that. And especially an old pair of eyes like mine just might not see them. And headlight glare is an especially driving hazard. There's those blue headlights I was talking about. And also in British Columbia, when I was a young fellow first driving, every year you had to take your car for a safety check. And you did it at a government-run facility. And one of the first things they always checked was your headlight aiming. Now, if you were really nice to them and didn't give them a hard time, they would the mechanics always had a screwdriver in their back pocket, and they would adjust your headlights if it just needed tweaking. And you could get out of there knowing that every year your headlights were then properly aimed. Since they've done away with that, they rely on, I suppose, on dealerships or mechanic shops, but not very many will check a headlight alignment unless you actually ask them to. You can do your own headlight alignment. On some of the modern vehicles, I'm not sure how that would be done because I haven't done that sort of thing for a long time, but they all have to be adjustable, and they should be adjusted downward so that the low beam is down below the grille height of oncoming vehicles. So that is a danger. It's a hazard on the highway that is from the new higher power blue LED lights. The bad. I'm trying to be optimistic here by saying that things are improving. Because LED lighting uses less energy, and that's one of the attractions of them, there's less motivation to restrain ourselves in their use. In other words, okay, we saved $1 million in electrical bills. Oh, let's go out and buy some more lights. And we add more lighting instead of saying, oh, okay, we've saved money. We don't really need more light. We just are saving money on the light that's already there. And unfortunately, people are just thinking that, oh, we'll just put on more lights or put more lights on a house, more lights in a business. And that, so we end up with the car lot mentality where everything has to be super lit up. We also started to convert lighting before any real major research was done onto the effects of these lighting. So before any regulations or even guidelines and recommendations could be made, people were changing over to LED lighting. Kits were being sold for headlights, which my pet peeve, as I've said. And so you end up with this sort of explosion of lighting in a lot of places, and also we just tend to overuse lighting and get excited. And I'm not against entertainment lighting in the sense that, like at Christmas time, they have these light shows and stuff like that. But there's smart ways of doing it, and one of the things that we need to think about is that the lighting should only light up the area that you want lit up, that is the purpose of the lighting, and not just lighting up the whole sky, lighting up your neighbors' yards, lighting up, there have been complaints, people will be living across the street from a building or an industry or a warehouse, and next thing you know, they're lit up as well, whether they like it or not. So we have to be considerate. And sometimes with the LED lighting, it's brighter, it's bluer, and so we need to consider that. But it's not as bad as the ugly, because I guess it's getting there. LED, the development of them is getting along where you can get different colors of light. So you can get they now can be dimmable, so they can also, you can get them in different temperatures. So the development of them is coming along. What we need now is guidelines and regulations that match that. Here's an idea what happens when you just, lighting is cheap. You can just blast the world with it. And it's okay if it's just a very short sort of time period, like a Christmas celebration or what other type of celebration that you might have going on for a short period of time. But unfortunately, these things, because they're cheap to run, they tend to be left on a lot longer than they need to be. And we'll get to the good. There is some good. LED lighting has developed rapidly over the last decade. That's one of my major points of optimism. We have LEDs of various lighting temperatures. So temperature is basically the color of the light, but it's also the energy that light is giving off. So when street lights first started to go into LED, they were all around 5,000 Kelvin. Some were even more. And those are blindingly light, especially if you come out of an area that's not lit. Your eyes don't adjust that quickly to the new bright light. And so you tend to be blinded temporarily. I live in Maple Ridge, and I live in a dark area, relatively speaking. And they built some new homes nearby, a block from my place. And so the contractors that build a house also have to put in the street lighting and sidewalks. That's part of the building codes and that. And they put the lighting in, and I was driving from my place to go to the store one night, and it was raining out, and I came to that street, and honest to goodness, I've calculated later that it took about 3 to 4 car lengths driving on this road before I could see where I had to make my next turn, which I knew that off by heart. I could almost drive it with my eyes closed. But having said that, I had no idea if there was somebody on the road. People, there's no sidewalks along there. So people walk their dogs on the road. Or some people even walk cats. I'm not too sure what that's about, but anyway. And so anyway, I thought these lights are way brighter than they need to be. So I phoned the lighting department of Maple Ridge, and to their, I sent them an email initially, and they emailed back and said, oh, well, the lighting there is supposed to be 3000 Kelvin, and it looks like the developer accidentally put in 5000 Kelvin. So anyway, they emailed me and said, we are out of stock on the 3000. We'll put 4000 Kelvin in immediately. And as soon as 3000 Kelvin lights become available, we'll modify them. And to their, I'm very grateful that they fulfilled that. They did change it. And I noticed the difference significantly when I drive down the street now that's been lit up, that boy, it's just so much more comfortable. It's still white light. I'd rather it was another color, but it was softer. It's a much better lighting condition, for, especially if you're coming out of a dark area into a brightly lit. So and that has to do with the temperature. So the higher the temperature, the whiter the light is, the bluer into the spectrum it goes. And when you come down in numbers down into the 3000, you're more in what used to be called a soft white, or almost getting to a yellowish light. LEDs are instant on and off, and that can be an advantage because street lighting especially, you can now turn a street light off or turn it back on and it's back on instantaneously. And that leads to another thing, that they're also dimmable. They didn't used to be dimmable when they were first made. So you could have dimmable lights in your house, so you don't have to have them, lighting up the whole area, like as if you're doing artwork or doing detail work or something like that, like a work light. You can have them so that they're more soft, more like in keeping with your decor and that. And of course, they're cheaper to operate than incandescent lights or fluorescent lights for that matter. And that's what's so attractive from a financial standpoint, and why LEDs are going to become more heavily used as we go on in history. This is a system which takes advantage of the dimmable and this is a terrible picture of it, but it's the only one I could find. ATCO is one of the commercial lighting companies, and they have a light on demand system, they call it. And it's where the lighting in a street is computer controlled based on the need. So if there's no cars driving on the road or no pedestrians walking, the lights go off. They could first dim, and then if there's no traffic for a pre-programmed length of time, the lights actually shut off. There was a pilot project of this. Oh boy, I'm going to forget the name of the city. It's in Alberta. My apologies. It might come to me before I get to the end of this. And the idea was that it saves electricity, because if there's nobody on the street, you don't really need to light it up. You save money. In the old days, that didn't work because these phosphor lights and that needed time to heat up. Like, they didn't come on instantly. LEDs do. You can have them so that if you have 2 sets of lights on every pole, one that would shine just on the sidewalks and one that lights up the street, you can have where pedestrians would trigger a walking light, but not the street light necessarily. And also, of course, we want them to be cutoff lights so they don't shine up into the sky. But having them dark is even the better solution than having them there. So if you don't need a light, why have it on? I mean, we've told kids, maybe people don't anymore, but I know I was told every time I left a room, if I didn't shut the light off, I was told to go back and shut it off. And that was just the way it was. But then my parents grew up with oil lamps, not lights. So burning oil unnecessarily was important too. So this is something that I didn't find out about till I think it was too late to really influence. BC Hydro had a program starting in 2018, they're replacing every street light that they own in British Columbia to an LED. And they have over 90,000 street lights in all of British Columbia. And you can tell them because they are all mounted on wooden poles. So if you see a street light in your neighborhood and it's on a wooden pole, that'll be a BC Hydro light, not a city light. And that'll be the type of light that they're replacing. And in Maple Ridge here, we have a mix of both. You can have street lights down a road until it hits a certain point of ruralness, so to speak. And then the only lights you'll see after that are occasional lights on a wooden pole, and those are all hydro lights. So they reached out to every area that pays the bills, which sometimes is just a rural area, but sometimes it's a small town and that. And they asked them what to select the wattage and the color temperature of the lights that are going to replace them. And my only beef was that they selected two possibilities. You either had 3,000 Kelvin or 4,000 Kelvin lights. So you either had warm white, which was not too bad. That's like, those are the temperatures of the lights that are in my neighborhood, or 4,000, which is brighter. And also they had a different wattage as well. So the different brightness again, but different temperature and different brightness. And apparently different municipalities and cities could have feedback to them. I never did find in my mailbox or anything from BC Hydro asking me to participate in any public forum or anything. So I really can't comment on how many of the public ever even found out about this plan. Both will give off a whiter light than the current HPS lights, the high pressure sodium lights, and they're around 2300 Kelvin. And that's why they are orange in color and that. But they use a lot less electricity. Unfortunately, every city that chooses, no matter what they choose, because it's going to happen whether they like it or not, they said the power rates would go up in those areas, which is counterintuitive to everything I've said. The LEDs are cheaper, but they have used the excuse that they have the capital expense of installing the lights and getting rid of the old lights. And therefore they have to up your bill to help cover this, even though it'll save them electricity. They seem to, that's the way of modern times, eh? Get less, pay more. So this just gives you a visual of this. There's a 3,000 Kelvin light on a same street corner and a warmer, softer light. And this is what they recommend for residential communities or in areas that don't have a lot of lighting. And then below you see the 4,000 Kelvin, much whiter than that, more for commercial areas, business areas, and that's what their recommendations are. And by the way, the link is down below there to go to their website and see that. And if anybody requests it, we can put that in the chat room and that to so people can get it and check it out. They can see what's been done, what's going to be done. Maybe even if their local areas where they live haven't made their minds up on lighting, they can have some influence on what is done in their neighborhood. And that you can't influence what you're going to pay, though. That's the Utilities Commission decision and not anything to do with us poor taxpayers. So to give you an idea with the street light with the 3000 K, and that IDA recommends street lighting to be 3000 Kelvin or below. That's the International Dark Sky recommendations. They think that 3000 Kelvin LEDs are going to become the standard everywhere. But they really would like to see 2700 Kelvin, which is very close to what the sodium lights were before. And 3000 though is catching on in lots of parts around the world. Quite a number of states in the United States have now adopted that as the standard. And I hope that Canada can see to adopting the 3000 Kelvin as the standard, as the high end of lighting. I don't know, there's a lot of people that push back and say they want brighter lights, but in fact, brighter lights just don't work out that much. I've also put the website down there for that site where I got this information from. I copied and pasted it right out of their site. So as you probably know, if you've ever had my talks before, I cheat as much as I can. So I grab things from other people. I'm quite unashamed of that. And that's the end of my show. So there you go.
Thank you, Lee.
I just got to hear it again.
So good. That was awesome. That was really great. I'm going to introduce now our final speaker, and please stay after Susanna speaks. We are going to be joined by Matthew Simone and Abby from SFU. But our final speaker I'm going to introduce is Susanna Nati, and she is our secretary, and she's going to talk about the Jim Bernath meteorite collection. And she's going to show us some meteorites and tell us a little bit about them. Thanks, Susanna.
Thanks, Haley. Hi, everyone. So I am going to introduce to you today a few pieces from the Jim Bernath meteorite collection. Now, how am I going to do that, do you wonder, being that we're all in different places viewing from our each individual homes? Well, I have a pen-like microscope. On the end is a little camera. This is attached by wire to the USB port on my computer. And when I zoom in with this microscope, the image appears on my screen, significantly enlarged. And when I share screen with you, then you'll be able to see what I'm seeing as well. So having said that, I don't see I'm going to share my screen. Okay, but first I am going to just do a really quick PowerPoint presentation. It's only about 6 slides. Okay. So this is the Jim Bernath meteorite collection. I do want to briefly talk about who is Jim Bernath. Jim Bernath was a member of RASC Vancouver since 1975. He was a collector of space artifacts and space memorabilia. He enjoyed taking his collection to libraries and schools. He particularly enjoyed sharing his collection with children. Unfortunately, Jim passed away in January of 2019, and on his passing, we at Vancouver Centre were able to purchase quite a few pieces of his space collection, which included his meteorite collection of about 20 meteorites. So questions we get often about meteorites are, what is the difference between comets, asteroids, meteoroids, meteors, and meteorites? So comets are the leftover material from the formation of our solar system. The primary difference between a comet and an asteroid is that comets are made of ice. So when comets enter the inner solar system and the heat from our sun starts to warm the comet, the ice melts into water, which then vaporizes into a gas and creates the tail of the comet that we all know so well. Asteroids, on the other hand, are primarily made of rock. Now, there is no defined size for an asteroid. It can range from a few meters in size to kilometers across. Meteoroids, therefore, are small chunks of rock, likely broken off from an asteroid. Now, meteoroids can be as small as a grain of sand or as large as a meteor across. Again, there's no defined size between an asteroid and a meteoroid. A meteoroid is a small chunk of rock, while an asteroid is a large chunk of rock. So if a meteoroid gets close enough to the Earth that it enters our atmosphere, it begins to burn up and fall to the ground. And that burning bright tail of the meteor is sometimes called a shooting star. Now, we have many meteor showers throughout the year. One of the most well known for us here in Canada is the August Perseid meteor shower. So if a meteor survives its trip through its atmosphere and hits the ground, it is then called a meteorite. And that's the extent of the PowerPoint presentation. So now I am going to move over to the camera. Now this camera is handheld. So as I zoom in and out, it will go fuzzy on your screen. Give me a few moments to correct that with the focuser. And so today I'm going to start with this stony meteorite. It is glued onto this metal, this piece of metal, sorry, so we don't lose it, because as you can see, it's not very large. I've got a loonie sitting here next to it, so you can see the size of the meteorite or see its relative size. This is a stony meteorite. It was seen falling the evening of December 15th, 1978. It was a bright fireball over the town of Nuevo Mercurio, Mexico. Let me say that again. Nuevo Mercurio, Mexico. Its main mass was originally estimated to be 14 kilograms, and so we've got a tiny little piece of it right here. Now you can tell the difference between a rock and a meteorite because of its burnt black exterior. So I'm focusing in. You can see its burnt black exterior. In comparison, apologize for shaking, I've got a regular garden rock right here. I picked up this morning when I was walking the dog. So here is a rock, not burnt, not black. Compare that to the meteorite, and you can see that it has a black exterior to it. Meteorites come in three main categories: stony, iron, and stony/iron. Not very imaginative names, but they also come, each category, in numerous subcategories. Iron meteorites are subcategorized by the amount of iron that's in them. Stony meteorites are categorized by the kind of minerals that are found in them, and stony/iron is, of course, a blend of the two. So this meteorite, again, is a stony meteorite. It's been identified to have H5 chondrite, which is a small amount of iron, but also olivine crystals and bronzite minerals. So I'm going to zoom in and hope that you can see some of those crystals in there. Moving over to the other side of it, you can see on the top, there's some crystals in there as well. I'm actually going to flip it over. Underside is glass, so you can see on the underside as well a little bit better because this has been sliced. That ring you see is the light from the camera. The crystals on the underside of this meteorite as well. All right, flipping it back. So again, this is a stony meteorite seen falling the evening of December 15th, 1978 over the town of Nuevo Mercurio, Mexico. I'm now going to replace that. Bear with me while I pull out the next meteorite. I apologize for the shaking. I have to do everything one-handed. This next meteorite is an iron meteorite. This is actually a slice, not a whole piece of rock. Again, there is the loonie next to it, showing the size of this meteorite that we have. This meteorite was found in 1838 in the Namibian desert of Africa. Now, one of the things that makes iron meteorites very unique are these lines that you can see. I'm going to focus in, bear with me. These are called Winmanstatten lines, named after the Austrian scientist who first discovered them. And if you were German speaking, that would be pronounced Winmanstatten. These lines are formed when nickel and iron are pressed together with enormous pressure and heat. Now, these lines cannot be recreated in a laboratory, and they have never been found in any rock on Earth. They have only ever been found in iron meteorites. It is believed that iron meteorites come from the inner core of large asteroids. Just as our own planet Earth has a molten iron core, many of the large celestial bodies in our solar system also have iron cores. So iron meteorites are believed to come as fragments from broken up asteroids from their inner core. Stony meteorites that I showed before are believed to come from the upper crust of asteroids. And then, of course, stony/iron somewhere in between. So again, these are Winmanstatten lines, an iron meteorite discovered in 1838 in the Namibian desert of Africa. All right, moving that over. Bringing in the next one. So I mentioned the three categories of meteorites: stony, iron, and stony/iron. Excuse me. This meteorite is an example of a stony/iron meteorite. It was discovered in 1951 in Esquel, Argentina. It was found by farmers digging a well. This meteorite is subclass pallasite, and it has yellow and green olivine crystals in it. I am going to zoom in so that you can see the yellow and green crystals. There we go. This meteorite, the Esquel meteorite, is considered to be one of the most beautiful meteorites ever discovered because of all the colors in it. And that's not my opinion. That is the opinion of the Meteorological Society. They've named it the most beautiful meteorite ever discovered. And I am absolutely thrilled that we have a meteorite of the Esquel in our collection here. So again, a stony iron meteorite discovered in 1951, containing yellow and green olivine crystals. Zooming out, I'm going to place that aside. Bear with me while I get the next one. Apologize for the shaking. I'm doing this one-handed. I have 5 meteorites that I'm going to show you today. So that was 3. I am now going to show you the 4th. Bringing it in. There it is next to the Luni, so you can see its relative size. Again, this is a slab or slice, of meteorite, not a rock. This is another example of a stony meteorite discovered in 1954 in Chico, New Mexico in the United States. What makes this particular meteorite interesting is that it melted as it entered our atmosphere. But while it was melting and traveling through our atmosphere, it caused gas bubbles to go through the meteorite. And the air bubbles or gas bubbles can often be seen in pieces of the Chico meteorite. And I'm going to zoom in because you actually can see the air bubbles that were created when this meteorite entered our atmosphere. There you go. So again, this is a stony meteorite discovered in 1954. in Chico, New Mexico, United States. Zooming out, taking it off and bringing in the last one. As you can see, this is really, really small. So I'm going to zoom in as best as I can. This is actually a moon meteorite, and we are absolutely blessed to have a moon meteorite in the Jim Bernath Meteorite Collection. This moon meteorite was discovered in 1998 in the Sahara Desert, Libya. Now, how did a piece of the moon end up in the Sahara Desert on planet Earth? Well, if you've ever had a good close look at the moon, you know it has thousands and thousands of craters. When a large asteroid hit the moon many millions of years ago, the ejecta from its impact would have propelled dust and rock out from the moon's gravity. Over time, these rocks and dust particles traveled to Earth, were captured by Earth's gravity, and made their way down through our atmosphere onto our planet Earth. So, and how do we know this is a moon meteorite? Well, we've been there. Apollo astronauts brought back brought back space rocks from the moon. Moon rocks, I should say, I apologize, brought back moon rocks from the Apollo missions. Those moon rocks were researched, and so they now know the minerals, chemicals, and isotope composition of those moon rocks. So when comparing it with this moon meteorite, or this meteorite, we can say we now know that this meteorite is a fragment of the moon. Zooming out. Again, it's really, really small, but it's wonderful to say we have it. And that concludes my presentation. I'm only showing 5, but again, we have 20 of them in our collection. And hopefully one day when we can meet in person, we'll have the Jim Bernath Meteorite Collection displayed in full so that all of you can come and have a look with microscopes and magnifying glasses yourselves. Thanks very much for your time.
All right, so
we are done, Matthew.
yes, hello.
All you now.
Hello, everybody.
Matthew and Abby.
Hi, yes, thank you.
Thanks, everybody.
Yeah, thanks everyone for tuning in up until this point. I was looking at the fact that we have.
Can't hear you, Matthew. You
Oh, he can't hear me? Am I muted? I think I'm unmuted now. They should be able to hear me, unless he can't. Can people hear me?
Matthew, I think you're muted.
They'll be able to hear me on the stream, I think, is what I'm hoping. Everyone will be able to hear me on the stream. So based on me being here,
You're still muted. We can't hear you.
I think everyone should
Here, the
no.
command center's muted.
Is the command center muted? Oh, let's see. It doesn't say I'm muted here.
Maybe
Still
he's
talking.
maybe he's on YouTube, on the YouTube channel talking.
Oh, maybe.
Can everyone hear me now?
Oh,
Yes.
yes.
Perfect. Okay. I think people could hear me on the stream, but I don't know if people could actually hear me on the Zoom call. So yes, everyone could hear me on the stream. Great. Okay. Anyways, hello everyone. I'm Matthew. I'm gonna see if I'll put this view back on gallery mode so you can actually see me. I'm up here. It won't hit me on my own speaker mode because I'm me. I'm the one hosting the stream today. Hi everyone. I'm so glad that everyone tuned in today. There's I'm looking at the YouTube stream right now and there's 100 people in here. What a bunch of nerds we are all hanging out on a Friday night talking about space. I love it. This is wonderful. So thank you so much, everyone. I'm joined by Abby, who's down there on the bottom. Hello, Abby. Abby, your background makes it look like you're actually in the Trottier Observatory. Are you in the Trottier Observatory right now?
No, I'm currently not, but that's a background. It's a perfect safe background.
I know, it is a great background, yeah. So So what we're going to do, just to wrap things up at the end, we're going to do like a quick virtual tour of the Trottier Observatory. I'm going to pretend that none of you know what this place is. And so we're going to do it kind of a start from scratch. It is the observatory that was built up at Simon Fraser University that was sponsored in part by SFU, and also a huge donation by the Trottier Family Foundation that helped to construct the observatory. And it's great. It's one of our pride and joys up at SFU because well, first of all, we always tell people that, when you're going to build an observatory, what you really want to do is have it away from lights, as Lee was talking about. Typically, you kind of want it away from water sources because they are cloudy places, like on the West Coast where it's constantly overcast. And usually you want it somewhere really high, like up in the mountains or in space, as we were talking about earlier with the James Webb Space Telescope. But the problem with that is that it means it's far away from all of you. So we had said we've constructed this thing up at SFU campus because then it's somewhere that all of you can actually visit in person. Now, of course, because of COVID, that was very difficult to do. So in the interim, we've been doing live streams called Starry Nights from the Trottier Observatory, where all of you can come and tune in remotely, and they've been amazing to do. None of us are actually there in person when we've been doing this, and that's the brilliance of this facility, is that it's all can be remotely operated and run, which is actually what we're doing right now. So we are tuned into it remotely, so we can do a quick tour of the observatory. Now, it is unfortunately cloudy, as we said, one of the things about it being on the West Coast, but we have a host of really cool pictures and images that we've taken with our own telescope up there at the observatory, and Abby and I are going to take some time to talk about some of those images. So if I have done this correctly, I'm going to press this magic button and my stream is going to switch over to the observatory in 3, 2, 1. Ta-da! Hopefully that worked. That's about the extent of my streaming skills, so hopefully this worked properly. I'm just going to watch the YouTube stream here for a second to make sure it actually went over, because it's delayed on my end. And hopefully this actually worked. Oh, it did! Oh, I'm so excited about that. Okay. So here we are looking at the stream from the observatory. And right now we're actually looking at the observatory computer's desktop, and you're looking at a piece of software which is called the Sky. And it's literally, that's what it is. This is how we control the telescope at the observatory. This yellow spot that's here right now is where the telescope is currently pointed to in the sky. And we have software that tells the telescope where and how to move. So this is this graph that you're watching right now is actually showing the real-time tracking of the telescope as it's moving. These are just tiny, minute vibrations that are just in the telescope as it's moving around. But it'll jump around when we move it from target to target. And literally all we need to do is click on a point in the sky. We hit the slew button, and our whole telescope moves around, which is pretty exciting. It's actually, I'll throw it, just a shout out to Lee for a second here, because the first time I ever set up my own backyard telescope, Lee helped me to put it together and set it up and stuff. And it's actually easier to use this observatory than it is my backyard telescope, because literally it's always set up every day. All we have to do is click and ready to go. And what we've done is we've turned on the interior lights at the observatory so you can see the telescope more clearly. Now, normally there's not this many lights that are on inside, because as we've been talking about, lights obscure our view of space. So usually we want it as dark in there as possible. But this is an actual live view of the inside of the telescope. And what I'm going to do, I'll try to point it somewhere in a direction that you can look more down the barrel of the telescope. So this camera is on the east wall of the dome. So what I'm going to do is I will turn around our sky here so that we're looking basically east. Here's north, because there is Polaris, so as part of Ursa Major, that constellation in the sky. So if I turn about 90 degrees in this-ish direction, kind of lower to the horizon around here, then we should be able to see the telescope kind of move in our direction. So here we go. Hey, that's not bad. And you can see the dome rotating behind us. So the dome is actually connected remotely as well to the direction that the telescope is pointed in. It moves a little bit more slowly. So the telescope itself can rotate 180 degrees in 1 second. Almost like a turret. It's pretty amazing how fast it'll turn around. You might ask, why would we ever need it to move that quickly? Well, sometimes if you're tracking a moving object like a satellite, we don't do that very often with the telescope, but it can be done. And in the past, we've also tried to use it to track the International Space Station, take images of the space station as well. We have a shroud right now around the telescope, so it's kind of this black sheath that's around the outside, and that also helps to stop extra light from shining in. That's our own sun shield, you could say, kind of like the James Webb Space Telescope, but around the outside of the scope, so we're not getting light pollution from campus, because there's a lot of lighting in and around campus. Like Lee was talking about, just right up at SFU, there's a lot of lighting on pathways and such that are there for safety, but they do sometimes interfere with our own imaging. I will try to lower where we're pointing in the sky right now to put as low as we can kind of get, and see if you can kind of look more down the barrel of the telescope. Let's see. No, it doesn't like being that low. Let's try going more here. Oh no, it's moving away. Okay, that's fine. It didn't like where I pointed it. If we go too low to the horizon, the telescope's like, nope, I can't point that low. Generally, we're looking at about any targets that we want to see need to be about 10 degrees off the horizon, and us to be able to capture them over the lip of the observatory dome. Where the telescope is pointed right now, you can see that there is a periscope that hangs off the side of the telescope. And actually, this is a really cool invention, and I just want to talk about it briefly. Normally, the eyepiece is up near the top. So if you wanted to look through the telescope, you'd actually get up to a ladder to see up that, to go and look through the eyepiece itself. But we were looking at this and we said we want, for reason of accessibility, for people to be able to come in to the observatory and actually be able to look through the telescope from a seated position. So we had a custom periscope that was built that hangs off the side of the telescope here, so someone can be seated and still be looking through the telescope. This periscope is actually two other telescopes that are just stuck together between one another. So this is another telescope here, and then that's another telescope off the edge, and they're basically all stuck together to create, it's a custom built periscope off the side in order to make that work. On the other side, I'm going to rotate us around the other way. Which way do I need to turn this here? I need to go back this way. Okay, one sec. I want to show you the other side of the telescope, because that is where our camera is. And then once we show the camera, I'll get Abby to start talking about some of our images. So let's move the telescope back in this direction. There we go. So on this side of the telescope over here, you can see that there's kind of like this disc and a box on this side. And that is our primary imaging camera. It's a special astrophotography camera that is cooled, so it has a cooled sensor in it. Why do you want to cool your camera? Well, when you're taking images during the day and you have a lot of light, you don't need to really worry about noise so much. But when you're doing long exposure photography in the dark, any little bit of extra heat that is in your camera can result in noise in your image. And so we intentionally will cool down the camera chip, usually to about minus 20 degrees Celsius. And that helps to clear some of the noise out of the camera. So we get really nice crisp images. And then you can kind of see there's like, it's hard, it's rotated a little bit more because there's a disc back there. I want you to see. This is this part here that you can see on the screen, this kind of darker contrast slit. This actually represents the opening of the dome. So we know that the dome opening is aligned with the telescope. And once it stops moving, I'll move it more in this direction. Or which way? I'm getting myself confused now. So which way I need to move the telescope? We need to move it back closer to north. Okay, let's go back this way for a sec. To about here. And go. There we go. So you can see there's kind of like a black circular part here by the camera. That's called the filter wheel. And what it does is it actually rotates different color filters around the camera. So the whole camera, the entire sensor, is used all at once. Now, in your typical color camera at home or on your phone, there are clusters of pixels that are actually assigned to different colors. So you might have, say, a 12 megapixel camera sensor in your phone, but those are actually split into groups of 2 green pixels and 1 blue and 1 red pixel. So you're actually only getting so much color or so much resolution per channel of color. So you're not actually getting a true 12 megapixel image. When we shoot with our camera here at the observatory, every single one of the pixels is used for each color, but that means we can only shoot one color at a time. So we'll shoot red first, and then green, and then blue, and we're rotating the filter on the camera. That filter only allows certain wavelengths of light to come through. And then in post-processing, we'll take each of the color channels, we combine them together, and we get a color photo. But that means that we are often sitting up for a lot of the night doing imaging. If you ever see a picture from space, it's never just one image. We're usually imaging for hours and hours and hours at a time. So one of those pictures, for example, Abby has done herself. So Abby, why don't you talk to us a little bit about your picture of, I think you did Messier 8. Is that correct?
Yeah, that's correct. That's the Lagoon Nebula.
Okay, let's find, here it is. It is a beautiful photo.
Okay.
You're probably getting it a little bit slightly delayed on your end, but it should be up now.
I can see it now.
Great.
And yeah, so what you're looking at is an image I edited. I imaged last year in the summer and edited afterwards. Yeah, so this is the Lagoon Nebula, and it's a summer celestial object, so you can see it in late summer. It's the best time for viewing it. So a lot of times taking these kind of images, because celestial objects are very faint objects, so you need to take long exposure, like Matthew mentioned, taking hours and hours of it. So what happens to the camera is that you're imaging an object, you're taking a lot of frames and you're stacking all of them together. And this is like how most people do astrophotography. And as for methods of stacking the image, some people, they would prefer using coding, like Dr. Joanna Wu, her preference is doing through Python. And for me and Matthew, we like to use PixInsight, because that's like how we started learning astrophotography. Yeah, so what you're looking at is Lagoon Nebula. It's M8 and it's a star formation region. And the bright pink and red color you see, it's actually from hydrogen. Yeah, and Matthew, why didn't you talk about your image? I remember you have a really, really nice image too.
Yeah, I can show one that we did. This one was one of my first attempts at imaging through the telescope, and it's of the Andromeda galaxy. So I'll bring that one up here. So this is a slice of Andromeda. Andromeda is the closest galaxy to our own, and it's actually, if you could see it with your eyes in the night sky, unaided with a telescope, it's actually about 3 times wider than the entire full moon. And we are due for a collision course with this galaxy in a few billion years, so stay tuned for that one. Astronomers like naming things very practically, so our future galaxy, when we merge with Andromeda, is going to be called Milkomeda. If you're an astronomer, you have 4 billion years to come up with a better name than that one. Anyways, so we're looking at the core of the spiral arms of Andromeda here. This is a total of 5.5 hours of exposure time. So remember, think of our telescope here, and I'll bring back the picture of it. It's basically, think of it like a rain bucket, all right? So if you've got a bucket outside in the rain, it is slowly going to collect water. The wider that bucket is, the more water it collects more quickly. So that's why when we're looking at telescopes in terms of their power, their size, we're looking at the size of the telescope in terms of its width, right? The size of the mirror, like we were seeing earlier in the comparisons between the James Webb Space Telescope and the Hubble Space Telescope. So our telescope at the Trottier Observatory is 70 centimeters wide. And those photons, the little bits of light, you can think of them as droplets, just like rain droplets. Well, they're so faint from a distant galaxy like Andromeda. Andromeda is about 2.4 million light years away. So we're only getting a few of those by the time they get here. So we really need to leave that telescope open to collect that light into our camera over hours and hours and hours. So this is a 5.5 hour total. You can get all the color that way as well. You can see here, if I'm able to zoom in, we're actually able to see these magenta clouds. Look at that resolution from this camera is amazing. So this is a magenta, basically a star-forming region. This is a nebula inside of the spiral arms of Andromeda. These dark arms here are raw dust and gas, interstellar gas that collects together into these clouds to form stars. Some of these bright blue points inside these are actually stars in Andromeda. So you're looking at a star in another galaxy. Some of the stars that you see in the picture are in the foreground, so they're actually in our galaxy as we're looking outside of it to see Andromeda. But some of these points of lights in the image are actually distant stars in the other galaxy. And in fact, one of them we've circled here, if I'm able to zoom into it. This is a star called M31V1. It is a variable star, and it is one of the stars that was used by Edwin Hubble, whom is the namesake of the Hubble Space Telescope, to measure the distance to the Andromeda galaxy. These variable stars, they're used as ways to measure distance across space. And the way to do that was done by was actually an astronomer named Henrietta Swan Leavitt. It's called Leavitt's law. So using that research that she created to use these stars to measure distance, Edwin Hubble was able to make the distance calculation, and that was the first time using this one star and a series of other similar stars in the galaxy that we realized we were not the only galaxy. So just that one star was a way to kind of unlock the whole rest of the universe for us, which is pretty amazing. That's when we first realized that there's more than just the Milky Way. And then, of course, since then, we have found billions and billions of other galaxies, which is pretty astonishing. That discovery was only made in 1926. So there you go. Yeah, one of the other core and spiral arms of the Andromeda Galaxy. Abby, what are we talking about next? What's the next one?
The next one is the Owl Nebula. There's a reason that I wanted to share this to everyone. If some of you may have attended Virtual Starry Night, we usually try to image brighter objects because we're taking live image. So it's really hard to view fainter object this way because fainter object requires long exposure. So yeah, as Matthew mentioned, or as I've mentioned earlier, that fainter object requires a lot of exposures. So Owl Nebula is one of the faintest object in the Messier list. So I think it's a good idea to share to everyone because yeah, people don't really view it a lot. Yeah, so this is the Owl Nebula we're looking at. It's one of the faintest Messier object. It has a magnitude of 9, so which means it's a very, very faint object comparing to, for example, Orion Nebula, which is around 100 times brighter than this nebula. So this is a planetary nebula. You can tell it by the shape. It's really round, and it's called the Owl Nebula because there are 2 dark patches on the nebula. So it actually looks like an owl. So that's where it got its name. Yeah, there you go. Yeah, it's really amazing. A nice color. Yeah, it is. And since we're talking about brightness, I can chime in a little bit. So I mentioned earlier, the Owl Nebula has a magnitude of 9. So visual magnitude, the bigger the number it is, the fainter the object it is. And comparing to Orion Nebula, which has a visual magnitude around 4, which is like way brighter. So every 5, every like 5 factors in between the 2 objects, it's like around 100 times brighter. Yeah, I think am I correct, Matthew? Did I fix it right? Yeah. Matthew, sorry to interrupt. I think someone in the chat is saying that they can't hear us.
I'm sorry, was I muted? This is something I need to stop doing. Okay, here we go. I'm back. Hello. So we're looking right now at the Trifid Nebula. I'll try that again. So here we are. This is the Trifid Nebula is actually a 3-part nebula. So it's 3 different things at once. So we're looking at, this is a reflection nebula, an emission nebula, and a dark nebula all at one time. So what are those 3 different types of things? So an emission nebula, like Lee was saying earlier, basically this is gases that are excited just like in high pressure sodium lights. So when gas is excited by energy, it will begin to glow. And so that's what's going on here in this picture. These are star forming regions. And so there are stars here that are being born inside of this gas cloud. And as they begin to glow, the gas starts to give off energy. And so the gas itself is beginning to glow with the energy that it's receiving from stars. There's also reflection going on in this nebula as well. So reflection, the gases in this case are not glowing themselves. They're not receiving enough energy that they begin to glow. Rather, they're just reflecting light from somewhere else in the nebula from these newly born stars. And lastly, it's also a dark nebula. And the dark portion of the nebula are just these dark filaments of gas here that are kind of separating the different parts. It almost looks like a giant beating heart. Although there is a heart nebula. That's not this one, but it kind of does look like a heart. You see the veins kind of on through it like that. There you go. Is there another one we wanted to cover, Abby?
I think we do have M52, which is a star cluster. Now that we have looked at the few nebula, we can look at some star clusters.
Sure. Here we go. M52. Go ahead.
Yep. So we're looking at M52. It's a star cluster in constellation Cassiopeia, so which is a circumpolar constellation, which means that you can actually see them throughout the year. Yeah, and I was part of this image. I did image it in the night, but I didn't process it. I remember it was really interesting, like, because I was pretty new to the observatory during that time, and yeah, so I just started learning all the operations in the observatory. So it was like really fun night, like learning everything and imaging and getting along with people around the observatory talking about astronomy. It was really fun night. Yeah. So yeah, this is an open cluster, as you can see from the image in here. So one of the interesting thing about this star cluster is that it's really hard to determine the distance away from Earth because it has a really high interstellar absorption line. So it's absorbing a lot of information, and it's just like really hard to determine the distance away from Earth. So now we have an estimation, astronomers have an estimation around 3,000 to 7,000 light years, but it's still not super confirmed. Yeah, this is like one interesting fact about the star cluster we're seeing here.
Yeah, and clusters like this, because they are like these clusters, these open clusters of stars are fairly new. And as a result, there's still a lot of dust in them because they formed from all this dust and gas. And as you were saying, Abby, that dust helps or basically absorbs some of the light. We call it dust extinction. And as a result, it sometimes makes it difficult to learn about these clusters or know how far away because their light is being dimmed by that interstellar dust and gas. Let's do some galaxies because we did Andromeda, but we've done some more distant galaxies as well. I got one here. This one is really cool. M82, the Cigar Galaxy. So the Cigar Galaxy is called a starburst galaxy. It's actually one of the kind of the main examples of a starburst galaxy. This means a galaxy that is actively generating stars at a far greater rate than a regular galaxy like, say, our Milky Way. So the Milky Way is producing, on average, about 3 stars a year are born within the Milky Way. Starburst galaxies like this can be creating, say, 10 to even maybe 50 stars a year. So the star formation rate is a lot higher. Usually it's because the gas and dust that's inside the galaxy, kind of like along the spiral arms that we were talking about in Andromeda, is being disturbed in some way. So it's being actively churned up so that that gas can mix together. It can begin to form stars. It collapses together to form more stars. And the general theory around this galaxy is that it is gravitationally being interacted with by another close by galaxy named M81, which we also have a photo of, so I'll bring that up too. And here it is. So M81 and M82 are quite close to each other in the sky, and that the gravitational interaction between the two is shaking up both galaxies so that they are creating stars at a far faster rate as well, which is really, really cool. So there are clusters of stars being created within the Cigar Galaxy that are 200,000 times the mass of our own sun. So giant clusters of stars. The one that we just saw, the other open cluster, might be a few thousand, but not hundreds of thousands. So we generally only see star clusters that big. We call them globular clusters. And one of the ways the globular clusters might be forming is in fact during the interactions with other galaxies. So we have some of those in our galaxy too, and it might be because in the past our own galaxy was pulled at by another in space, or maybe even collided with other galaxies in the past as well. That is a really clear picture of MED2. And again, all taken with our own telescope. Abby, is there another on your list?
I think that's all on our list. But yeah, in general, yeah, I think it's really nice. We can look at a lot of nice pictures and imaging them and learning to process them. It's a really good experience and rewarding experience.
Yeah. We also do some other cool things. When there are the rare astronomical events, we can sometimes image them as well. So the summer of 2020, everyone may have remembered that we had Comet Neowise come traveling through our solar system. It is a long period comet, so likely orbits the sun maybe once every 10,000 years or so. And we were able to track it enough in our own telescope to be able to take a picture of it. So I am credited in this photo, but I think that's generous from Joanna, who did most of the work to make sure that we could take an image of this one and collect the light together from it. So the stars are streaky in this picture because rather than tracking the stars for the image, we're tracking a moving object. And so as a result, the background is streaked out. The actual head of the comet that you can see here, that kind of green, we call it the coma, at the head of the tail is about 5 kilometers wide. So it's basically a big flying rock all the way through space, which is pretty cool. And then we also do science. Not often, but we sometimes do research with our observatory as well. So I'll bring up one of the examples. This is a Hertzsprung-Russell diagram, it's called, of a star cluster M67. This is done by Bryce Adam, who I believe is an astronomy student up at SFU. And but basically what we're doing is with our own telescope, we'll sometimes show how we can do this kind of research. In this case, look at the colors of stars, and by the colors help to determine the age of the star and whether or not has it evolved into something called a red giant toward the end of its life. So we are able to do that work with our telescope as well. But again, the main kind of purpose of the observatory is not research, although it can be done that way, but outreach. And so that's why we do what we do. And so speaking of which, make sure to keep in touch with us because we hopefully will be doing more of these in the future, either in person, depends on how things go with COVID and everything else, but also as well virtually. So you can always tune in to our virtual streams as well, and hopefully be able to tune into those streams so we can still have you a part of our online community looking at the stars. So I think that wraps up everything. Haley, do you want to do like a wrap up ending?
Maybe Alan. I just wanted to say thank you to everybody. It was amazing. I think it's a great event. A good kickoff to the new year.
Yes, excellent. Very enjoyable. Thank you, everyone.
I'd love to hear any feedback if anybody wants to add anything in the chat room. Just trying to plan virtual events for 2022, because I think that we will be doing a little bit more virtual events over the next couple months. So if anybody has any ideas, suggestions, please share in the chat room. And would love to know, who you are, if you're a student, if you're a member of RASC. Let us know and how we can help you and guide you in your astronomy. So thank you.
All right, thanks everybody. Have a great night. Thanks for tuning in.